This is the problem that I gave you the answer, and I explained what the problem is. So there was some small flow of an ideal gas through the intervening space in between two porous plates, and you were asked to calculate what is going to be the temperature distribution as a function of the flow rate of the gas, its temperature, the thermophysical properties, and so on. So we have seen how equation of energy can be used whenever we have conduction and convection both present, and a simple geometric analysis of the problem based on what we have done before, that is, the shell balance would not be appropriate. And I spoke at length about the dissipation function and so on. Today I'm going to look at a slightly different problem, which would require more thought, more understanding and approximation that is needed in order to obtain an engineering solution for a specific problem. So this is something which is very common to many practical situations where you have a hot surface which is in contact with a fluid, surrounding fluid that is at a different temperature, and you would like to find out there's no applied flow, and it's the only way the heat can be extracted out of the hot plate is by natural convection. So the flat plate is heated to a temperature of T0, that's the temperature. It is suspended in a large body of fluid. So you could assume that it's a very large body of fluid. It extends all the way up to infinity for convenience, for mathematical convenience, and it's at a temperature of T1. And fluid obviously near the plate will get heated up and will rise due to buoyancy, and that's how natural convection takes place. And we need to find out the heat loss on the system variables. And the important part here, the important line here is that the free convection form of the equation of motion is to be used. So we would have to first find out what the free convection form of equation of motion is, and then write that in conjunction and solve it in conjunction with the energy equation, and try to at least see from our order analysis, magnitude analysis, what kind of a relation or correlation you may expect for the case of free convection from a vertical plate. So there are certain assumptions. So the first assumption is straightforward. It's a geometric one. The dimensions in the x direction, that is a plane perpendicular to the screen that you are looking at, is quite large, and Vy and Vz. So you have some Vy and definitely a Vz. Both are functions of y and z only. So as it rises, it's going to probably accelerate, and there will be viscous forces which will try to retard the upward motion. And of course, the Vy is also going to be a function of y as well as z. So the second assumption that one can make, that's also understandable, that Vy is going to be small. So the air surrounding it almost moves straight up, and y component of the equation of motion is to be neglected. So it's the z component of equation of motion that is to be taken into account, and the y component can be neglected. But we understand that the velocity in the z direction, Vz, is a strong function of y. It's going to be zero due to no slip condition at the plate air interface, and it's going to be again zero at a point very far away from the plate. So the profile, exaggerated profile, would probably look like this. Why I say exaggerated? Because this is the portion which is going to probably take place at a point closer to this. So you have zero velocity at this point and zero velocity at this point. So somewhere in between it will pass through a maximum, and the location of the maximum is to some extent exaggerated to give you a better picture, a better understanding of the process that is taking place. Similarly, the temperature is going to be T0 over here, and it's going to be T1 at a point over here, and as you could see, the two temperature profiles that I have drawn at two different Z locations, they essentially tell you something about the formation of the boundary layer. Once again, the way the temperature varies over the distance over the y is to some extent is greatly magnified, because we all know that the temperature is going to vary within a thin boundary layer, and beyond that boundary layer, the temperature is simply going to be equal to T1. So this is a more realistic representation of the temperature profile. But the two profiles which I have shown over here demonstrate that the temperature, apart from being a strong function of y, it will change with z as well. So that's the reason why these two profiles are provided. However, they are representative schematics only. So we still do not know how they are going to change, but we understand that the temperature is going to be a function of z as well as a strong function of y. Vz is going to be a function of z as well as it's going to be a very strong function of y. So these are to be taken into account. And there are certain definitions which you are already aware of. The beta is the coefficient of volumetric expansion, the coefficient of volumetric expansion due to a change in temperature. So if we write the buoyant force, it's simply going to be rho g delta V, that's the buoyant force, due to the increase in temperature of a portion of the fluid, which would result in a change in its density, and the buoyant force per unit volume is simply going to be rho g beta delta T. So that's going to be the buoyant force. It becomes more clear if we look at something which is to some extent fundamental, and the fundamental one is known as the Bosnius equation of motion for forced and free convection. So how the equation of motion together with equation of energy can be different based on whether we have free convection or forced convection. So what happens in non-isothermal flow? Both the rho and mu, they will change since they are a function of temperature as well as pressure. But let's leave the pressure right now from our consideration. Let's talk about the pressure, I mean the density and the viscosity only, as they vary with temperature. So the variation in rho is extremely important, since it's going to give it gives rise to buoyant forces, as what we have seen over here. Now we would like to quantify that as much as possible, and with some approximation. So the buoyant force, it's essentially a body force, so it must appear automatically in any equation which is similar to Navier-Stokes equation. So what can be done is one can use the equation of state and insert it into the equation of motion. For example, this form of variation of density as a function of temperature can be substituted into the Navier-Stokes equation. So this is simply a change in density as a function of temperature. And this rho bar, the bar essentially means that it's the average density between the two temperatures, and we have already defined what beta is. The point to note here is that everything, wherever you have a bar, that means it's evaluated at some average temperature, which is denoted by T bar. So when this equation, the equation that you see, which is obvious, it must go in place of the rho g term of the equation of motion. You remember, in the equation of motion, there is a term on the right hand side which is denoted by rho g and is known as the body force term. So the body force now has to be modified in order to take into account the buoyant force. And when you do that by making some sort of an approximation, as you see here for rho, that's known as the Bosnius equation. But the point to note here is that the rho is not going to be inserted to the left-hand side, which has experimentally traditionally been shown to be less important as compared to the rho g term on the right-hand side. And I will clarify it a bit more in the next equation itself. So this is the form of the equation of motion. So you remember this d dt, which is the substantial derivative of velocity. This is the pressure force, the surface force, and what you get here is an additional force due to the buoyant force that I have discussed so far. So why it is important, or rather why it is important, or rather not important to include rho bar in here? So that would be an obvious question. And what would be the form of this equation when we are talking about free convection or when we are talking about forced convection? So let's first talk about this term. This term, which represents buoyant force, and obviously in forced convection, the entire motion of the fluid is most likely be due to the pressure which you apply on the system. That's what forced convection is all about. You force the liquid to move through a pipe or a tube. You force the fluid to flow over the flat plate with some velocity. So it is the pressure force most likely in conjunction at times with the gravity force that is going to predominate, and therefore, and this is the viscous term which would obviously be there. And in forced convection, you also have to consider the velocity, the convective transport as well. So this is to be kept in mind. But this buoyant term, which would rather be very small in forced convection. So whenever a flow takes place over a flat plate, due to forced convection, the buoyancy-driven contribution to that flow can safely be neglected. So this is going to be the form for the case of forced convection with which we are familiar with. On the other hand, if we are talking about free convection, and free convection we know are characterized by the absence of any pressure gradient induced flow. So this part is rather going to be small for the case of free convection. Additionally, if I make both the terms to be equal to 0, then what we are saying is that we are simply saying it is the hydrostatic which is balancing the pressure generated due to gravity, and in absence of any temperature gradient, these two terms will simply cancel each other, and there would be no flow for the case of free convection had there been no temperature gradient. So in free convection of these terms, this can be taken to be very small in comparison to this, whereas in forced convection, this term can be taken to be small as compared to the free convection part. And once again, in free convection, the left-hand side is probably going to play a lesser role, since the velocities and therefore the convection associated with the flow would be small in free convection. So with the simplified Bosniesque approximation, you now can have an equation of motion, and you know what to do for the case of free and forced convection. So this is sufficient for us now to go and try to see what would be the equation. So the equation of motion, as I have said, it could be this. The left hand side, I have kept these two terms. Whether I will neglect them or not, that will come later. But it's the pressure term has been dropped. The rho g term has been dropped. The shear force term or the viscous force term will have to be kept in this. But this is the Bosniesque form of the equation of motion for the case of free convection. Any question?
Hello, sir.
Yes, please.
Sir, the substantial derivative part, can you please tell what are the conditions when we neglect which terms?
I am not saying that I have substantial derivative in the equation of motion. What you see here of this substantial derivative, first of all, I have used a steady state assumption. So if it is steady state, then obviously the del v z del t term is neglected, and I have the other term that I have neglected is vx del v z del y. I have initially mentioned that the z direction, the plate is too wide, So there is no velocity to consider. So therefore, Vx term, the second term, when you expand the substantial derivative, has been neglected. So if I expand the substantial derivative and I am writing it for the z component of motion, so it would be del Vz del time plus Vx del Vz del x plus these two terms as you see over here. The first term del Vz del time is set equal to 0 since it's steady state. The second term Vx times del Vz del x is 0 since nothing changes in the x direction from the statement of the problem. So these two terms will be left on the left hand side, which denotes some convection, which because in free convection also you have some velocity. How and how much that velocity will affect the transport of momentum, that we have to independently evaluate. But these two terms, that's why I have kept in the equation of motion. Does that answer your question?
Yes, sir.
So we know that this could be small, but I do not have enough data information to neglect them. And on the right hand side, I have these two equations, and this is the buoyant transport of momentum which we have kept in there. And this is the standard form of the energy equation. Once again, the Vx term has been neglected, and there are no viscous dissipation since the velocity is small, and no heat generation. So this is what these three equations have to be solved in order to obtain some sort of an idea of the heat transport in such cases. So if I look at this, and of course there are a number of boundary conditions which have to be specified for this to solve this. The important part which I would like to highlight over here is that this you haven't seen previously. A temperature term appears in the equation of motion, and the velocity obviously appears in equation of energy. All the equations that you have seen so far, there was no temperature term in the equation of motion. There were velocity terms on both the equations. So there was a coupling between, so equation of motion, the way to do this is equation of continuity, equation of motion, and then equation of energy. If you do not consider the last term of the equation of motion that we see over here, then the equation of motion can be solved independently in order to obtain the expression for velocity, and that expression for velocity can then be substituted to equation of energy. So there is a one-way coupling in most of the situations that we come across. Independently evaluate velocity and then use that expression for velocity to find out what is the temperature distribution in a system. Provided rho, mu, etc., Cp, etc., do not change appreciably for the temperature ranges that we are considering. So there is always a one-way coupling. This is the first time that you are exposed to when there is a both-way coupling because of the appearance of temperature in the equation of motion. So you cannot solve Vy or Vz independently because the temperature term appears over here, which means that because of this two-way coupling, both equations will have to be solved simultaneously in order to obtain a comprehensive solution of temperature as well as that of velocity. Any question about the both-way coupling? Okay, so please feel free to ask me questions if you have, and I will try to explain. Anyway, so we now have to identify what could be the possible boundary conditions. The first one can write it for y equal to 0, I can say that all velocities Vy, Vz, all would be zero because of no slip condition, and temperature would simply be equal to T naught of the plate, which is which is essentially saying that temperature is continuous across any interface. And since I have mentioned about y equals zero, I should write talk about something at y equals infinity. So at y, as y tends to infinity, what can you say about the conditions that you would expect? What is going to be the value of Vz? What is going to be the value of T? The value of T is obvious. It's simply going to be T1. And what is going to be that of Vz? At a point far from the plate.
0.
And the third one is when we are talking about this region, that means when Z tends to minus infinity, because what is going to happen to Vy, Vz, and T. At a point far below over here of the plate, relative to the plate, what would happen to Vy, Vz, and T? First of all, Vy. What would be Vy? See, anything that goes up is to be replenished by some fluid from the bulk. Okay, and this is going to go up to this point where Vz is 0. It would probably look something like this, just a representation. So what is going to happen to Vz at this point? Would it sense that there is a plate well above this point which is causing a motion over here? So what would this Vz be?
I think 0.
You're absolutely right. It is 0 since the presence of the plate far above it is not going to be noticed. It's not going to be felt by a point which is way down there. On a similar logic, you can say that Vy at that point will also be equal to 0. Okay, so that's straightforward. There obviously could be no Vy at that point, and it's just still air where there is no effect of temperature variation or other temperature-induced density variation, and thereby a buoyancy-driven flow. And this T would obviously be equal to T1. So with these three boundary conditions and these two governing equations, one would attempt to solve the temperature profile and try to obtain, as we engineers try to do, is to get some relation for the heat transfer coefficient, convective heat transfer coefficient for the natural convection case. More importantly, the way we handle these cases is we would like to find out what is the Nusselt number correlation for Nusselt number relation for such a situation where there is no imposed pressure gradient driven flow. Now, to solve this is kind of problematic. So one would rather go for some order of magnitude analysis and try to see what is going to be the form of it when you non-dimensionalize it, and see what if your understanding can lead you with some simplification of the equation. So this problem is also a problem in BSL. So you could look at it for the complete solution, but there are certain dimensionless variables which were defined. So for the temperature, it's T0 minus T1, sorry, T minus T1 theta, the dimensionless temperature, is T minus T1. This is not important in understanding it. So I will skip this part as much as possible. I would rather want you to concentrate on the way these things are done. So this alpha is it's mu by, or Cp mu by K, or alpha is K by rho Cp, that you know. This mu is the viscosity, H is the length of this. So your Z variable has now been replaced by zeta, your Y variable is replaced by eta, and so on. And the phi Z and phi Y, these are the velocity, these corresponding to velocity. Once again, as I mentioned, you do not need to, there is no understanding part involved here. Just for completeness, I am writing it. And everything is there in BSL. So with this, now we can write the equation del phi y so this is your y and z, as you could see from here, z and y. Phi y and phi z are the vz and vy. And interesting thing is the appearance, automatic appearance of Prandtl number in these expressions. Once I write this, I will explain. And that is probably more important than the equations itself. Okay, let's look at the first equation. Once again, I point to it, the appearance of temperature in the equation of motion, which couples it to the energy equation where theta appears. And of course, the velocity terms are there in both the equations. So in terms of velocity, they are coupled, they are always coupled, but in natural convection, due to the presence in temperature also, there is a both-way coupling. The left-hand side of the equation of motion refers to convective motion, convective transport of energy. The right-hand side, there is a diffusive or conduction and the buoyancy-driven flow. If you look at the equation which I have shown previously, there is definitely a difference. What you do not see is I have dropped this term in my new equation. But can you see what is it okay if I drop this term from the equation? These are conductive transport of energy in the direction of flow. If I go back to the picture over here, this is the picture. So del square Vz by this entire thing is nothing but the conduct in the z direction. Am I correct in dropping this term? Am I correct in keeping both these terms? I would like to hear from you. Let's talk about the combination of these two.
Sir, in the left-hand side, I think we have not dropped del Vz by del Z because Vz is also there. So that term is not small.
Right. So large, but del Vz del Y is large in comparison to del Vz del Z. So this is same as the boundary layer analysis which we have done before, as a result of which none of the terms on the left-hand side can be dropped. You are absolutely correct. Now let's come back to the right-hand side. Here we have conduction in the y direction, and this is conduction in the z direction. Okay, so it's just a flat plate. This is the y direction. This is the z direction. And of course, temperature is going to be a strong, very strong function in the y direction because of the formation of the boundary layer, thermal boundary layer. Whereas in the z direction, the principal mode of heat transfer is going to be convection, and the v and the velocity would not vary, or rather the gradient would not be as much as this. So this will predominate as compared to this term. Any question? Is that clear to all of you? That the conductive transport of momentum would be more in the y direction as compared to the z direction, because in y direction it changes from a value equal to 0 to some higher value in a thin layer close to the plate, and therefore the principal transport of momentum in the y direction has to be by conduction, by molecular transport of momentum. So this term will be present in the equation. If I apply this, if I apply the same logic to this equation, to the energy equation now, there also we would see that the temperature is going to be a strong function of y. So this part is going to be large as compared to temperature variation with respect to z, so as compared to this term. So if I compare only the part of this term, this is going to be far greater than this term, whereas we know that Vz is going to be large as compared to Vy, which essentially tells me that I cannot drop any terms on the left-hand side. When we come to the right-hand side, it's the conduction of energy. Now, if you look at the conduction of energy, the conduction of energy is going to be in this direction, mostly in this direction, primarily or predominantly in that direction, because the temperature is a strong function of y and a weak function of z, which essentially tells me is that this term, both of these terms in the equation of motion and equation of energy can be neglected, which has given rise to this expression, where everything that varies with respect to eta, that means y, has been kept, and anything that varies with z in the conductive transport of momentum and conductive transport of energy have been dropped. And the second thing is that the Prandtl number has appeared in the equation of motion itself. So when we talk about phi y, essentially the velocities, and phi z, they are going to be functions of. Can you tell me what they are going to be functions of by looking at the three equations that I have written over there? Which independent parameters they are going to be functions of? if you look at this
Yeah,
expression.
theta and zeta.
Eta, zeta. Anything else that you think it is going to be a function of?
Theta.
I understand that you are tempted to think that it is theta, but theta is going to depend on eta, zeta. So when you say phi is going to depend on eta and zeta, implicitly what you are saying is that the theta is also taken care of. So I would rather change my statement. Phi y, phi z, and theta all will depend on eta and zeta. So that part I think is clear. Are we missing something? Are we missing at least one more in
So Prandtl number.
Prandtl number? It has to be Prandtl number as it appears in the equation. Now, you tell me, Prandtl number, is it related because of the Prandtl number? We know that the flow in the case of free convection is rather slow. So therefore, the terms in which Prandtl number appears, the left-hand side will generally be rather small. And we understand that because the left-hand side of this equation, which is essentially this part, these two, they refer to convection. And in free convection, the flow is rather slow. So the effect of the entire left-hand side, be it momentum transfer or be it energy transfer, will be rather small. Everything is going to be governed by the viscous forces and buoyant forces, which are essentially the first term on the right-hand side and the second term on the right-hand side, respectively. So any term where Prandtl number appears, the effect of that will be, as you can see in this, will be rather small. And if I set them exactly equal to 0, what kind of a flow is that? There is a name for that kind of a flow where the convection is unimportant. We have been using that term again and again in this course. If you set convection component to momentum transfer equal to 0, what kind of a flow is that? It is called creeping flow. So in creeping flow, you do not have any contribution from the left-hand side of the equations of change and equations of motion, principally equations of motion, and that's why it's called the creeping flow. The essence of this discussion, therefore, is that phi y, phi z, and theta will continue to depend on eta and zeta, but its dependence on Prandtl number would be rather small. So that's some sort of a simplification which we can mentally make, that phi y and phi z and theta are principally going to depend on these two, and its dependence on Prandtl number is going to be rather small. Just need 5 more minutes. So with that knowledge, what we are going to do is, as engineers, once again coming back to the application part, I would like to find out how much of heat, average heat, that I'm going to lose from a chimney, for example, or from a vertical pipeline through which you are transporting a gas, or how much of energy you are going to gain if this pipe is used for cryogenic applications, for transport of cryogenic fluids. So it's the average one which is important. How much heat is going to lose, how much heat it is going to gain, and of course, using Fourier's law and averaging the delta T over delta Y at Y equal to 0, which is the heat flux at the interface, and this is simply the definition of the average temperature difference, average temperature gradient at the interface. This is the temperature gradient at the interface. And when I integrate it from 0 to h with 1 by h outside, I am simply finding out this entire part is nothing but the average del T del Y. So if I multiply this average del T del Y with K, then I would obtain what is the heat flux that you would obtain for heat transfer from this. So once I non-dimensionalize this, and this part I will let you you should see it from the boards from your textbook. It comes to be K T0 minus T1 B by mu alpha h to the power 1/4 0 to 1 minus del theta. This is the temperature by del eta, which is which is the y direction. Since it's at y equal to 0, so it's eta equals 0 times d zeta. Now we have understood that theta was a function of eta, zeta, and Prandtl number. Now you tell me what this Q average is going to be a function of. This we have understood. Okay. So what is this entire thing Q average is going to be a function of, apart from whatever parameters that you see over here? Is it going to be a function of eta? Look at the definition.
No,
But
sir.
it is a function of Prandtl number and theta.
Can you repeat once again, please?
Sir, zeta and Prandtl number.
It's going to be a function of zeta and Prandtl number. You are probably saying that it's not going to be a function of eta because you have specific. So it's not going to be a function of eta. Is it going to be a function of zeta? That's the next question. It's a definite integral between two specific values, 0 and 1. Definite integral over zeta. So is it going to be a function of zeta? You have specified it eta to be eta at 0. So therefore you are taking eta out of this functional form. But this is also a definite integral over zeta. So the functional relationship should also not contain any zeta as well. So what is this going to be? So if I write this entire, so this is simply going to be a constant, some numerical value to this. So the way it's expressed is this Q average is going to be some constant, which is this, which is what you see over here. And then you have K by H, T0 minus T1. And the new number that appears, which you are aware of, is Grashof Prandtl to the power 1/4. You know what is the definition of Grashof number. You can always see it in any text. But this C, it must be a function of Prandtl number for the discussion that we have over here. Agreed? Any question? We understand that this definite integral will be a function of eta, zeta, and Prandtl number. It cannot be a function of eta. It cannot be a function of zeta. So whatever value that you get will be a function of Prandtl number. So this so-called P that I have written is going to be a function of Prandtl number. The question is it going to be a strong function or is it going to be a weak function? That is the question. What is your idea? I go back to this. I emphasize that Prandtl number, this entire thing essentially is related to convective transport of momentum. We realize that in natural convective heat transfer process, the flow is small. The role of convection is small. So all terms which appear in equation of motion, they will have little contribution in the overall value of theta. With this logic, when we impose on here, we realize that this C is going to be a function of Prandtl number. However, because of the nature of the flow in natural convective heat transfer, this is only going to be a weak function of Prandtl number. So you are safe to write a relation like this, which you have obtained semi-analytically using some of the approximations that I have already discussed. For example, neglecting convection in the y direction, convective heat transfer in the y direction, and so on. So this C, which I must evaluate, this C is not that important. This C anyway is going to be a weak function of Prandtl number. So why not the engineering solution to this problem is, then why not you do some experiment at different values of Grashof and Prandtl number, different values of Reynolds number, and see what is the value of C. And once you obtain some value of C, use that for any such combinations, since it's going to be a weak function of Prandtl number. So your fluid may change, your conditions may change. This value of C, from our analysis, we anticipate it will not change much. So let's look at some of the experimental measurements. So these are the values of Prandtl number which you see, 0.73 to 10 to the power 3. That essentially covers all fluids that we know of. So if you do that, the value of C is almost same, 0.6, around 0.6, except for low values of Prandtl number. Okay, so for most of the cases, the 0.6 is a safe choice for the value of C. So what you get then, therefore, is a relation for natural convection that you have obtained without going to go through a complete solution, just based on your physical understanding of the system. And this is what I am trying to tell you time and again, that transport phenomena should let you think about the physics of the problem, which would allow you to arrive at solutions which may not require involved math in order to get the final solution. So your understanding and common sense can take you a long way, and this is a beautiful example of how that is done. And therefore, when you look at any natural convection formula right now, you know that the reason why this C is given as constant value, even though we understand it is a function of Prandtl number. Any questions? If not, then I will introduce the concept of. I'll quickly solve one more problem about force convection, and then go into the thermal boundary layer concept. Whatever I have said over here, you could see that the departure becomes significant as the value of Prandtl number is reduced. Can you name some fluid for which the Prandtl number is very small? What class of fluids will have a very small Prandtl number, and that has a significant, tremendously important industrial use? The type of liquids characterized by a very small value of Prandtl number is the liquid metals. So the type of fluid, liquid metals, they traditionally have very small value of Prandtl number to the range 0.01 or even lesser than that. But we all know the application of liquid metals as a they have very high thermal conductivity. So they are perfect material for extracting heat from nuclear reactors. And with our analysis, we won't be able to apply this sort of a relation for the case of liquid metals. So apart from liquid metals, any other fluid, we should be able to use the concept that is developed in this course. And I will tell you on Friday's class that how to handle liquid metals. So is there any question that you would like to clarify, any point? Okay, we'll meet on Thursday, Friday again for the rest of our heat transfer part.
Excuse me, sir.
Yes.
Excuse me, sir.
Please go ahead. Aman.
Yeah, sir. Actually, I have a concern regarding the second test. Like most of us have booked tickets on 30th to return to the campus. Sir, can it be shifted? Can it be preponed?
I can do that, but that it should. I understand your concern and the problems that you are facing. So I can do it on a weekday before 30th in the evening. So 27th is a Sunday. 28th I can have it. I can arrange for it because you have to, since you are traveling on 29th and possibly on 30th as well. So I can do it on 28th if I can find a slot in module. Is that, do you, the rest of the students agree with him on this?
It works for me, sir.
Okay, so I will send a general mail to all of you, all the registered students, that we will have the test on 28th evening if I get a time from the module, and then 28th we'll have a test based mainly on heat and mass, based only on heat and mass transfer, and then during the stipulated time, whatever be the stipulated time, we'll have our final test of 2 hours duration.
Okay,
so tentatively, that is what we are fixing right now, but it will all depend on availability of time in the module and any other concerns that any student has. All right. Thank you so much then. Bye.